Hey, you guys, please remind me tomorrow that I want to go over with you the concept of percent yield. And we're going to do this specifically related to the values or the data that you collected in lab on Thursday. Even though I told you to remind me, you're probably going to forget just like me, and that will make me sad. But we'll figure it out. Somehow we'll get it done. Okay, so on to what we're going to be talking about today. We are going to continue stoichiometry, and all of you did really well on Friday with figuring out how to do mole-to-mole conversions. And really, the key to understanding all stoichiometry, but in particular mole-to-mole conversions, is that there are two elements that you can't forget. And that is what I have written right here. Number one, make sure that you balance your equation correctly in the first place, because obviously your coefficients are vital for this whole process. And number two, that it's all about ratios, exclamation point. Never forget that concept. And don't forget that that ratio remains fixed. With every single equation, it's going to have its own set of ratios of ingredients. So please keep that in your brain when you move forward. And don't forget, in fact, some of the key metaphors that we have going in here. This is clearly a birthday cake that I've just drawn here. And what I want you to think of is always have birthday cake on your mind, because the concept of ratios works really well when you think about baking. If you're baking a cake for a family of 4, you're always going to have the same ratio of sugar, eggs, and water and oil. And if you're baking that a set of cakes for, say, the whole Choate campus, you're not going to vary that ratio or your cake's going to be screwed up. You're just going to multiply that ratio by some factor to take into account that you have more mouths to feed. But the ratio remains fixed. You'll have the same ratio of sugar, eggs, water, flour, etc. Okay, so with that in mind, never forgetting that, let's move on to the next concept, and that is, what do you do when you have a mass to mass stoichiometry problem? How do you handle something like that? Well, before we go too far, I actually want to create a concept map of sorts to help you understand this. So it's going to start off with a circle here, and I'm going to write inside this circle. You'll always be given a particular mass in these types of problems of a substance. So let's just call it the mass of the given, whatever the given substance is that you're talking about here. And you're going to take that mass and you're going to do a mole conversion. You always want to go through moles. That's the key element to this thing. You have to go through that process. So obviously you're going to consult the periodic table in that process. And then in the next situation, then once you have those moles in hand, and I'm going to go to a rectangle here, then you're going to have the number of moles of whatever that substance was. So moles of your given. And then you're going to do the next thing, which is a mole conversion of sorts, but it's one where we're going to focus in on the mole ratio. And you can only get that from a balanced equation. So you do the mole ratio, and you do that so that you can generate, let's see, I'm going to go with a triangle, I guess, here. Hope I can fit it in here. And this would be, now, if you've done the mole ratio, this would be the number of moles of whatever it is that you're focusing in on. So let's just call that the moles of the unknown. So that would be whatever one of the reactants or products is that I've asked you in the question, what that value will be. Okay, and then we go from that, we go back into another mole conversion because we want to go back to mass. We don't want to keep it at moles. And so with that, I'll have a different shape. Let's do a stop sign, because this would be the end of the problem. And in this situation, then, once you do the mole conversion, then you'll be at the stage where you have your answer, which is the number of moles of whatever your unknown is. Okay, so there you have your concept map of what it is that we're going for. Actually, it begins here with mass of the given, goes through the moles of the unknown. So let's take a look at a problem. Let me take a moment to write out the problem and then come right back on screen. Okay, so here's the problem. Determine the mass of carbon dioxide when 0.85 grams of butane reacts with oxygen. So when something's reacting with oxygen, we're talking about it actually undergoing a combustion reaction. And so it's vital that you actually first get the balanced equation for this thing. So we're going to go with our butane, which I gave you the formula for right there. So C4, oh wait, oops, mistake, boom, get rid of that thing. Butane is C4H10, my bad. So C4H10, and we're going to combine that with oxygen, and that's going to form, this is burning a hydrocarbon, so you should always know that it's going to produce the same thing, carbon dioxide and water. And the states of matter aren't important here, but they're all gases. Okay, but for this problem, they're not terribly important. But this is not a balanced equation. I'd actually like for you to pause the screencast for a moment and jot some notes down, see if you can figure out the balanced equation. So go ahead and pause right now. Okay, I'm assuming that you paused, you're coming back in, and if you had done this right, you would know that there'd be 2 of those butanes, 13 of our oxygens, 8 of our carbon dioxides, and 10 waters. Okay, so just like I said, if you go back to our previous page here, we're going to start off with the mass of a given, and in fact we are given the mass of 0.85 grams, and we need to figure out the number of moles of that given to start off this whole thing. And I think you all know how to do this, but I'm going to go through this process and go ahead and do it for you. Okay, so this is the setup. My equivalency is obviously right here. I got this number by consulting the periodic table, multiplying carbon times 4 and hydrogen's molar mass by 10 to get 58.14. This is my given that I have here. And when we crank this out, we get the answer of 0.015 moles of my C4H10. Okay, so somebody's texting me here. Anyway, I'll go back to that later. Now, like I said before, if we're going to get the number of moles, doing a mole conversion, we're now at the red box here. And now we're going to determine the mole ratio between the moles of what we had and the moles of the unknown that we're going for. And in this case, remember that in the question it asks, we want to know the mass of carbon dioxide that is produced when you have that much, 0.85 grams of butane. And you can see here that if we look at our mole ratios, we have 2 butanes for every 8 carbon dioxides according to our balanced equation. And that's going to be a really important thing because we're going to use that in our next conversion here using the ratios. So we're going to take what we just calculated, the 0.015, and that's the number of moles of our butane. And we have our equivalency, which is our mole ratio, and that's going to be 8 moles of carbon dioxide to every 2 moles of butane. Could I have done 4 to 1? Sure. Just nice to keep it nice and even though, so we don't mess with anything. And when we crank that out, we're going to get that you would produce 0.060 moles of carbon dioxide. Okay? And then again, go back to here. Once I have my moles of my unknown, which is my carbon dioxide, I'm going to do a mole conversion to figure out the number of moles of my I didn't mean moles. Chang. Naughty. I meant mass of my unknown over here. Sorry about that. And so let's go ahead and crank that one out. That means we're going to take this 0.060 moles of CO2, we're going to do a mole conversion based on the molar mass of CO2. So we take 0.060 moles of carbon dioxide. I'm going to blow this up so it's easier for me to write. I consult my periodic table, and this is my molar mass for carbon dioxide. So my equivalency would be over 1 mole of CO2. Again, it's important that I started with moles, so that means my moles have to be in my denominator here. And when you put this into your calculator, you get the answer of 2.6 grams of carbon dioxide. And that, friends, is the answer. Okay, so again, it asked what's the mass of carbon dioxide when you burn 0.85 grams of butane. You go through these 3 different steps, and that's going to give you your final answer that you got right here. Okay, let's do a similar thing, but instead of doing mass to mass, we're going to go mass to volume, or volume to mass. And this too, I'm going to put together a little scheme to help you to see where we're going with this, just like I did with the mass to mass. Alright, so you can see it's actually almost identical. We start off with the mass, go through moles, mole ratio, and then the only difference here is at the end, you're taking into account that this is happening at STP, and you're talking about gases here, and we all know that 1 mole of a gas at STP is always going, regardless of the gas, it's always going to occupy 22.4, oh chang, where's my undo, 22.4 liters of that gas. Okay, so let's take a look at our problem. Alright, so here's our question. Find the mass of benzene required to produce 2.66 liters of CO2 gas at STP, obviously that's going to be a vital piece here, from the combustion of benzene. So it's asked a little bit differently, but it's really not a very different problem from what we just did moments ago. So let's take a look at how we do this. The first thing we need to do is create our balanced equation. So I'm going to go ahead and create the equation to have you balance it. Again, I want you to pause this once you've written down the equation. Try to balance yourself and then come on back. Okay, I assume that you're back with me now. And if you did so, you would find that you'd need 2 of these guys, 15 of these fellas, 6 of these boys, and 12 of these gals. Alright, so now I have my ratios set, and I can start attacking this problem. Alright, so most importantly, don't forget that I'm given the 2.66 liters of CO2 gas. So I need to convert that 2.6 liters of CO2 gas into moles. This is happening at STP. Alright, so I know that 22.4 liters is 1 mole of any gas, and I'm going to use that in my conversion. So this looks like 2.66, oops, I'm not drawing anything, 2.66 liters of carbon dioxide, and my equivalency is 1 mole of carbon dioxide over 22.4 liters of CO2. And when I complete this, chuck it into my calculator, I get this value. Okay, and then don't forget, if we go back to our scheme that we have over here, once I've done the mole conversion, now I have moles of my given. I need to now consult my balanced equation to do the mole ratio to figure out how many moles of unknown I need. So when I look at this, if I have 2.66 liters of CO2 that were produced, there's my CO2 with a 12 in front of it, and I want to know the amount of benzene that I needed to burn to get that. And you can see here I have a 2 in front of my benzene, so that means we have a 6:2 CO2 to benzene ratio. And I'm going to go ahead and use that in my next thing. So I'll take my 0.119 moles of CO2. Don't forget that I just got that right here. Okay. And I'm going to do my mole ratio, so I have 2 moles of my benzene to every 12 moles of my carbon dioxide. Right? Again, I got that from here. There's my 2, and here's my 12. And when I put this into my calculator, I get 0.0198 moles of benzene. And then, of course, I'm not done, because once I have my moles of my unknown, I need to do the mole conversion again to figure out the volume of my unknown gas. So let's go ahead and go back into here. So this is my number of moles of the gas, my unknown, which is the benzene. And so I'm going to take this number, and I'm going to convert that using a mole conversion piece again. So, oh, hold on a second. No, did it ask for? Didn't ask for volume. It asked for mass. Geez, I have to go back. Bing. Chang, are you messing this thing up just to mess with kids? I am. Jeez. This is what I'm going to be covering in class tomorrow. I just totally messed this up. There you go. I'm going to erase that. I'm going to erase all this there. You don't need that yet, because I want to go right to mass of my unknown, since it did ask in my problem to give me the mass of benzene. Sorry, kids. That's why this is going for 2 minutes longer than I wanted it to. So then I'm going to take my 0.0198 moles of my C6H6, and I'm going to do a traditional mole conversion here. I use my periodic table to figure out that if I had 1 mole of C6H6, it would be 78.12 grams of C6H6, and that's going to be 1 mole. And when I put this into my calculator, I get 1.55 grams of C6H6. That is my answer, and I am done.